Hi, in this video I'll show you how to calculate the pH change of a buffer solution. So let's say our example is when we're adding base to a buffer solution. And the question says, calculate the pH change that results when 0.010 moles of solid NaOH is dissolved in 1.0 liter of the 0.50 m HAC/AC minus buffer. Now AC is short for acetic acid. And I think you know that NaOH is a strong base, so it will completely dissociate. Now I think you know that solid NaOH is a strong base, so it will dissociate completely. And large amounts of OH ions will have an affinity for the H plus in acetic acid. Now, although HAC is a weak acid, OH is a strong base, which will cause the reaction to proceed to completion. And our equation will be HAC, which is HC2H3O2 plus OH minus yields C2H3O2, which is acetic ion, plus H2O. Now, when we're calculating the pH, we have two steps. First, we need to create an RBCA chart to show the HA consumed and the AC produced, which is acetic acid and acetic ion. We need to show that, and then we need to use the right chart to show the new concentrations and use the HH equation for the pH. So let's start with the RBCA chart. RBCA. We have initial. How much moles do we have initially? Remember, RBCA, when we're doing Rebecca chart, we're using moles only. And it told us that we have 0.10 moles of NaOH. No, we don't need that for now. We need 0.50 molars. And since it's 1 liter, 0.5 mole will be equal to 0.50 moles. Right? Moles divided by 1 liter is equal to 0.50 molar. Now, OH minus, we said we have 0.01. And since it's moles divided by 1 liter, it's going to be 0.01 again. And over here, we start with 0.05 since it's for AC, HAC, and AC buffer. So our concentration for C2H3O2 at initial will be the same as our acetic acid. Now, water, we will not care. So let's, when we're doing RBC chart, we need to figure out what's limiting reactant, and we're going to subtract both of these by the smallest number, minus 0.01, minus 1 over 1, 0.101, and minus 1 over 1. Remember the coefficients. Everything here is 1, which makes our calculation easier. Plus 1 over 1, 0.01. Now 0.5 minus 0.01 is 0.49 moles. This will turn into 0, and this will turn into 0.51 moles. Now again, moles divided by the solution, which is 1 liter, will be molar. So this is also 0.49 molar of HC2H3O2, and it's also going to be 0.51 molar of C2H3O2. Now we can use a Rice chart, RICE, and the reaction will be HC2H3O2 plus H2O, which forms H3O plus C2H3O2 minus. Now initial is going to be 0.49 molar. We're going to bring it down, 49 molar. And this, we're going to bring this down over here as well. So it will be 0.51 molar. H2O, we don't care. And the concentration of H2O plus, we start off with 0. This will be minus X. This will be 0.49 minus X. This is going to be plus X, X. And this is going to be plus X. It will be 0.51 plus X. And remember, you must convert to molar to do these Rice charts. If we're not given an easy to work with number like 1 liter, then you're going to have to be dividing these moles by the volume to solve for the molar. And now we can find the pH by using our HH equation, which is pH equals pKa plus the log of the conjugate base divided by our acid, which pH will be pK. Let's see, what is this this equation produces H3O plus. So we're just going to take the Ka of acetic acid Ka for acetic acid is 1.8 times 10 to the fifth. Ka equals 1.5 times 10 to 1.8 times 10 to the fifth. Is it 1.8 times 10 to the fifth? It is 1.8. Alright. Now we're going to take the negative log of that. Negative log to find the pKa. 1.8 times e to the negative fifth, which is going to be 4.74 plus log concentration of A minus at equilibrium is going to be 0.51 minus x. Now, because our K is so small, we can simply ignore this x. So on top, it's just going to be 0.51, and then divided by the concentration of HA at equilibrium, which is 0.49 minus x. Since our Ka is an extremely small number, we can remove this minus x as well. So down here will be 0.49. And that will just give us our pH. So let's plug in our calculator. 4.74 plus the log of, on the top, 0.51, on the bottom, 0.49, which will give us a pH of 4.76. And that is our pH. Okay, now let's also quickly calculate the original pH, right? Because we're asking for the calculate pH change. So we need to find the initial pH. And the initial pH, we're just gonna use our acetic acid and add it to water along with our conjugate base. So it's gonna be HC2H3O2 plus H2O. This donates water. This donates a proton, which turns into C2H3O2 minus plus H3O plus. Now we plug into our concentrations, and we're gonna use a rice chart to solve for pH. And we're given with 0.5 and 0.5 molar. So 0.5 molar and 0.5 molar. Don't care about water. Minus x, 0.5 minus x. This will be 0 plus x, 0.5 plus x, plus x, and this will be x. Now our Ka is 1.8 times 10 to the negative fifth. So because Ka is so small, we can delete this plus x and delete this minus x. This is basically saying Ka is equal to 0.5 plus x times x divided by 0.5 minus x. Products over reactants. Now, since this is removed and this is removed, we have 0.5 divided by 0.5, which is 1. So we can cancel this out, leaving us x. So K is equal to x. And our x is going to be our K value, which is 1.8 times 10 to the negative fifth. Now, negative log of our x gives us our pH. So negative log of our Ka, which also happens to be the pKa. So our negative log will be the same as our pKa above, which is 4.74. 4.74. Now, what is the pH change? To calculate for the pH change, we're going to use our after. After we added the OH, what is our pH? Our pH is 4.76. Subtracted by the original. What is the original before we added our concentration of OH, NaOH? And that is 4.74. So our after subtracted by before, it gives us a change, which will be 0.02. So our change in pH is an addition of 0.02. Thank you for watching.